Hello everyone, my name is Tunai and the title of our work is Size-invariant detection of marine vessels from visual time series. In this work, we want to identify the presence of vessels of different sizes because they have been associated with negative anthropogenic impact upon marine environments. We want to create a system that can identify vessels of different sizes even under different viewing conditions. Some of the challenges that we faced are related to the size of these vessels, which can range from extremely big, like in this cargo ship, up until pixel-level vessels that are hard even for a human being to identify and sometimes need to use motion to be spotted. Other challenges relate to the shapes and colors of these vessels, the weather in the scenario, and also how the surface of the water looks like. We noticed that end-to-end object detectors like FASTER, RCNN, and RetinaNet do a great job in identifying medium and large size boats, as in this example where FASTER RCNN could easily identify this vessel. However, object detectors really didn't perform well when we were working with small marine vessels like this one, which was just not identified by them. Therefore, our system uses small time series to detect motion. We use 3 images captured 5 seconds apart from each other and 2 main modules. One that uses object detectors for the identification of medium and large size boats, and a novel module called the Detector of Small Marine Vessels, the SMV. And then we put their results, their detection together. The DSMV starts with a novel bidirectional Gaussian mixture model, where we use 2 frames for the creation of a background model and a 3rd frame to look for deviations of this model that would indicate foreground. We start with frame number 1 and frame number 2, and then when we get to frame number 3, we already have a good model of the background. Therefore, we can find motion triggered sets of connected components like this one that show where the boat that we're looking for is. We then use morphological operations to filter the results and create a bounding box around it, which we call the FMBB, forward motion bounding box. We then do the reverse trajectory. We use frames 3 and 2 to create a model of the background, and then frame 1 to do the detection. That's why we call it bidirectional GMM. The result of the backwards motion is called BMBB. We now have to match these 2 bounding boxes together. We use our first environmental assumption, which says that these boats are likely not going to move vertically, so we set a horizontal detection band, and inside of it we do template matching using cross correlation. Now we have 2 match bounding boxes. We now determine, using these 2 bounding boxes, what we call the temporal tunnel, where we expect that the boat is going to be on the mid-image. This is assumption number 3. Since the speed of this boat should not change in these 15 seconds, it is reasonable to assume that it's going to be placed roughly in the middle of the temporal tunnel. And this is going to be our 3rd bounding box. Our 4th assumption relates to the content of these bounding boxes. So if a group of 3 patches, if a group of 3 bounding boxes is invalid, their content is not going to look alike. Therefore, if you calculate the mean squared error for this group of patches, it is going to be way higher than that of a valid group. Therefore, our 4th assumption is that the patches have similar content. The last filtering step of the SMV consists of a custom-trained deep learning-based image classifier that is going to differentiate between patches that represent background from those that represent vessels. We manually annotated roughly 2,000 patches of vessels and 2,000 patches of background. And as you can see in this example, the SMV was able to correctly distinguish between patches of background in yellow and patches of vessels in red on this blended image. We create and make publicly available 2 datasets of monitoring images showing vessels. D1, which possesses vessels of diverse sizes, and D2, which is composed exclusively of small-sized vessels which are way harder to identify. We then use these datasets in conjunction with state-of-the-art object detectors to evaluate the performance of our system. This table shows that the proposed hybrid approach always outperforms its object detector-only layout counterparts. For example, the gains between configurations 4 and 14, considering dataset D1 and an IOU threshold of 0.2, were of more than 16%, but the real potential of the DSMV is noticed in the results of dataset D2, where we have a gain of more than 112% between configurations 2 and 14, and an overall gain of more than 89% in the whole dataset. Thank you.